Welcome to Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. There are certain things I check on when I prepare for every episode. One of those things is the status of the Vera Rubin Observatory and its upcoming large survey of space and time. The camera was delivered a while back, and first light images could come any day. Getting us just that much closer is news that the 3-ton camera has been mounted on the telescope. Touted as the size of a small car, they will be swinging this camera around the sky from night to night with hair-fine precision. I have to admit, I failed to understand just how massive this camera is going to be until reading that it has been mounted news showing it being the size of a small car. This got me to thinking, how massive is this telescope? For years, folks have been telling me not to worry about the impacts of Starlink and other small satellite constellations on astronomy because Starship will be able to launch telescopes like Rubin into orbit like it's no big deal. Version 3 of Starship is quoted as being able to launch 100 tons to low Earth orbit. Telescopes generally don't like to be in low Earth orbit. They like to be either a bit higher or preferably out at the gravitational sweet spot beyond Earth's orbit, where they are technically orbiting the Sun. For Starship to launch massive telescopes to these orbits, they will need to be well under 100 tons. And it turns out that Rubin weighs in, or rather masses in, at 350 metric tons. This means that story that Starship may accelerate our loss of observational capabilities, but will also allow us to launch massive telescopes just like we build on Earth, is only half true. We're going to lose our skies. We're not going to be able to just mount thrusters and gyros on everyday observatory telescopes and put them in orbit, though. So next time you hear about the launch of Kuiper, OneWeb, Starlink, or other satellite constellations, ask yourself at what cost. To quote Into the Woods, "It's nice to know a lot, but a little bit not. And I'm not always sure I like knowing the consequences of all these satellites we're launching." Rubin will give us first light soon, and I wish it had a quieter sky to peer into. But we do what we can. And in this episode, we're going to talk about the new science we are still able to get as we both look out across the universe with space telescopes like Euclid and ground-based instruments like DESI, and what we can also learn as we look back at our world and remember it's the only planet we know of with intelligent life. All this and more is coming to you right here, right now, on EVSN, a product of CosmoQuest X, and supported through you on Patreon. At the beginning of our last episode, I mentioned that we had just learned that new work by the Dark Energy Spectroscopic Instrument, or DESI, had provided hints that our universe has a changing density of dark energy. But I needed time to look over the research. Well, I've looked, and the news is kind of cool, especially if you like mysteries. As the story goes, back in 1998, 2 different supernovae research teams did a fit to their brightness versus velocity data and found the expansion rate of our universe, which is the source of that measured velocity, appears to be growing over time. Our universe appeared to be accelerating apart. This was unexpected, and in a moment of lack of creativity, that thing causing the universe to expand at an accelerating rate was named dark energy. Not our finest moment. Initial results seem to indicate that the amount of energy in every cubic meter of space is about the same as a few protons. And this density is constant with time, but trying to measure what's going on in the distant universe isn't all that easy. And better data would require new instruments. And those new instruments are starting to get us results. First on the scene is DESI. This instrument is very carefully documenting where galaxies and cold neutral clouds of gas are located by looking for the galaxy's light and then looking for how those cold clouds are absorbing that light from some galaxies' emission lines. By mapping out the evolving distribution of our universe's mass, they are able to compare what we see with the expected distribution based on what we see in the cosmic microwave background radiation, that wall of light that was produced when our universe cooled enough to form neutral atoms. The slight temperature variations we see in the light reflects the distribution of mass at that moment. And the distribution of galaxies and cold gas we see closer to us reflects the distribution of mass at the times when the light was emitted or absorbed. When the DESI team combined their early results with other data, they found evidence that the changing distribution of mass is best matched by models that have dark energy that may be weakening over time, or that its energy density, the amount of energy per cubic meter, may be decreasing over time. These are still preliminary results. Within error, the data can also be fit by models with constant amounts of dark energy, just not quite as well. More data from DESI is coming, and now all of us have even more reason to be excited for this instrument. And other data sets are also on the horizon. ESA's Euclid mission is starting to return its own maps of galaxies and more, with its first data release coming mid-March. So far, they've classified 380,000 galaxies and 500 gravitational lens candidates. We also saw the launch of SPHERE-X, a small NASA space telescope that will be mapping the first galaxies to light up the universe. While it hasn't completed calibration yet, early uncalibrated images demonstrate its ability to make out faint, distant galaxies. If I were a betting person, I'd be putting down money on the evolution of dark energy getting sorted this decade. As new information is published, we'll bring it to you right here on EVSN. There are certain key questions that go hand in hand with mapping the changing nature of dark energy. For instance, we're looking to the early universe to see when the first galaxies came to light and how fast they and other structures grew into systems we might see in our modern universe. And while DESI, Euclid, and SPHERE-X are out there mapping how structures evolve, it's JWST that is showing us how they formed. Prior to JWST's annoyingly early Christmas Day launch, for which I remain bitter, prior to that, we had thought galaxies started to light up around 1 billion years after the universe formed, give or take a few 100 million years. We thought it would take time for small galaxies to grow into large galaxies and for the opaque neutral gas that fogged up outer space to be cleared away by galaxies' ultraviolet light. We thought wrong. JWST has been finding early galaxy after early galaxy and consistently pushing backwards the time of first galaxy formation. One of these galaxies, JADE's GS Z13-1, was first identified in 2022 and appears to be shining from when the universe was roughly 350 million years old. It also appeared to be a fairly foggy gas-free region. Neither the existence of a large galaxy nor a fog-free region made any sense with our old theories. So new data was taken with JWST's near-IR spectrograph to see if the observations were right. And the results appear in a new paper in Nature and confirm this galaxy is shining from when the universe was a baby, from when the universe was just 330 million years old. According to UK researcher Roberto Molino, quote, "The early universe was bathed in a thick fog of neutral hydrogen. Most of this haze was lifted in a process called reionization, which was completed about 1 billion years after the Big Bang. GSZ 13-1 is seen when the universe was only 330 million years old, yet it shows a surprisingly clear telltale signature of Lyman alpha emission that can only be seen once the surrounding fog has fully lifted. This result was totally unexpected by theories of early galaxy formation and has caught astronomers by surprise. Lyman alpha gas comes from hydrogen gas and is from the 2-to-1 energy transition in that hydrogen. This ultraviolet light is associated with star formation in high temperature environments. While it's entirely possible this is a weird system that is doing something special in the early universe, it is astounding that we found this baby galaxy so quickly after JWST started to do science. One of the more surreal aspects of JWST images is that infrared light can pass through a lot of dust and gas, allowing us to see galaxies that were previously hidden. New images of Herbig Haro 4950 resemble a weirdly abstract Christmas tree. A ring galaxy ornaments the end of the jet as other systems peer out through the nebulosity. The clouds we see are formed where a young star's jet pushes the interstellar media. This is just a chance alignment. But sometimes random chance can produce something really cool to look at. After a break, we're going to look back to Earth and our changing world. Stay tuned. We live on a geologically active, rocky world that is uniquely shaped by a combination of water-driven weather and complex life. Currently, we're the only world we know of capable of supporting humans without requiring advanced technologies and mitigation against radiation and the certain death of environmental toxins. Understanding our world is a basic need if we want to preserve and protect life, but in many ways the politics of humans make studying our world weirdly difficult. Earlier this week, I got a notification from NASA that one of their funding programs had to be canceled because of DOGE's cuts to U.S. aid. In order to help support humanitarian efforts, NASA has provided researchers who use satellite data to study our planet. No U.S. aid means no humanitarian efforts, which means no Earth science research in those parts of the world. While I am fundamentally more upset about the cuts to HIV drug disbursement programs and the elimination of nutritional support for starving children, I am also annoyed that research that could have a long-term impact on the well-being of a large population is just not going to happen. So far, NASA hasn't experienced the same society-harming cuts we've seen other agencies experience. But these are the cuts relevant to our show and my career, so they are going to get mentioned. And now we're going to move along and talk about wildflowers. Seriously, wildflowers. While a lot of Earth science involves individual researchers and teams of researchers going out into the field to directly study our planet's Earth, air, water, and life, this isn't the most effective way to study things that happen over large areas or large periods of time. Consider, for instance, the importance of flowers, bugs, and other pollinating critters all coming onto the scene at the same time. The emergence of animals and plants each spring is linked to the changing amount of light we get with the changing seasons and also to changing temperatures. While our orbit is keeping sunrise and sunset on a millennia-old schedule for now, climate change is causing temperatures to rise earlier than we've seen historically. And this is causing things like flowers to emerge earlier than ever before. We're also seeing changing weather patterns that are bringing water to the deserts and triggering rare mega blooms of flowers. The initial emergence of blooms is often noted by volunteers reporting what they see while out on a hike using either citizen science apps or social media. Monitoring these reports are researchers like NASA-funded Jocelyn Angel, a scientist at the University of Maryland and Goddard Space Flight Center. She is using data from a camera on the International Space Station that looks at the chemistry of light reflected off Earth. Flower pigments come from 3 chemical families which each absorb light in unique ways that we can see from space. This means it's possible to see in the combined light of vast swaths of Earth the distinct signature of flowers. The more flowers stand in the sun, the stronger the signature will show up in the camera's data. On the other side of the U.S., NASA-funded researchers at the Jet Propulsion Laboratory have developed an airplane-mounted camera that does similar work but can capture more details from its closer to Earth perspective. This airplane-based instrument was, according to NASA, quote, able to capture 97% of the subtle spectral differences among flowers, leaves, and background cover, soil, and shadows, and identify different flowering stages with 80% certainty, end quote. This data will aid in everything from farming to land management to predicting changing fire risks. The emptiness of our world is perhaps one of its least appreciated features, and also means there aren't people looking everywhere all the time. While there are some areas that have populations in numbers I struggle to comprehend, with megacities that have populations greater than the entire American Midwest, the world is, by and large, unpopulated. And this makes satellite usage all the more important for tracking our world's ever-changing features. And this is equally true for studies of shifting icebergs and shifting seamounts. It turns out that it is possible to map the floor of the ocean using satellites, not with images or with radar, but rather with gravity. The SWAT satellite was designed to map out the surface height of water for use in tasks like measuring how flooding propagates along rivers. It turns out, however, that the average height of water on the ocean corresponds to the pull of gravity beneath the ocean. Rocks, minerals, and other features are denser than water and can compress the water with their pull. SWAT is sensitive enough to detect these variations. A collaboration between NASA and the French Space Agency, with contributions from Canada and the UK, allowed SWAT to release its first map of the ocean floor in December, and is now working to refine that initial map. While gravity measurements don't give us the same detail we get from boat-mounted sonar, the data is good enough to aid in finding the best places to lay cables and to help us study currents, the geology of how the world's crusts have separated over time, and more. There had once been a goal to map the world's seafloor with high-resolution sonar by 2030. And that task is one we are now admitting will not be completed on time. But these satellite maps help us set priorities and fill in our gaps with low-resolution data that is better than no data at all. Data set by data set, we're realizing that we want more ground-based data, but we don't have the resources. So space-based data it is. One of the most important things many researchers want to monitor is the emission of greenhouse gases. The problem we run into is wind and resolution can smear out the emissions of smaller contributors like smaller power plants. A new study from the Chinese Academy of Sciences combines satellite data from NASA's Orbiting Carbon Observatory, OCTO, and EPA's Clean Air Markets Program data to look at emissions from 1,060 U.S. power plants. They determined that satellite data alone underestimated emissions by as much as 70%, with only 72 large plants accurately getting measured. Through modeling, they could improve things somewhat, but ultimately, in order to track who is and isn't following clean air regulations and working toward agreed-upon Paris Climate Accords, we're going to need to have more sensitive spacecraft that both have higher spatial resolution and greater sensitivity in terms of parts per million that can be measured. One of the things that caught my attention about this research is this was Chinese-funded researchers focused on climate change, using federally funded U.S. data to study emissions in the U.S. And this is research that U.S. researchers likely can't do using U.S. funding after recent cuts and the release of restricted vocabulary that prohibits the discussion of climate change in many different contexts. We live in unusual times. Our world is changing in response to human-made pollutants, the redistribution of flora and fauna driven by human activities. And at least a large swath of America has been turned into a parking lot. Defunding research into these changes won't make them go away. But it will make it harder for us to prepare effectively for the rising water levels, increasing weather and fire hazards, and other issues that will just make it harder for us to subsist on our planet. At least we now know the Chinese Academy of Science is funding some of this research for us. After another break, I'll be back with this week's Tales from the Launchpad. This week, Eric is off getting ready to move, so I am going to be reading the rocket news. On March 14th, Rocket Lab launched the Susanoo 1 satellite for IQPS. Let's watch the launch.
5, 4, 3, 2, 1.
Beginning picture.
The mission was named The Lightning God Reigns and is the first of 8 dedicated launches for IQPS that Rocket Lab will conduct. On March 16th, Russia launched 3 Rodnik communication satellites into orbit from their Plesnik spaceport. The launch was conducted by an Agara 1.2 rocket, which is still relatively new. The Rodnik series of satellites are used for military communications. On March 17th, Rocket Lab launched another batch of Kinney's satellites from their Mahai Peninsula spaceport. Let's watch the launch.
5, 4, 3, 2, 1.
They were contracted to do 5 launches, and this was the 5th and final launch. Fittingly, it was named High 5. The satellites are used for Internet of Things communications and support the Argos system, a collaboration between NOAA, EUMETSAT, and ISRO. For our 3rd Rocket Lab launch of the episode, they sent up 8 CubeSats for German company Aurora Technologies. Let's watch the launch.
5, 4, 3, 2, 1. Liftoff.
Beginning pitch over.
Electrons, click the power to see for the launch pad.
as usual, it lifted off from their Maihai Peninsula spaceport, specifically Pad 1B. Its second launch in March 2025. The CubeSats each have an infrared imager and will be used to identify wildfires from space. The company plans to have 100 satellites in its final constellation. On March 30th, ISAR Aerospace conducted the first launch of their Spectrum rocket from their Norwegian spaceport. Let's watch what I will call a launch. ISAR Aerospace is a German company that launches from Andøya, Norway. Their rocket is fueled by propane and liquid oxygen, an unusual combination for liquid rockets. The company prepared extensively for the flight, and it carried 2 real satellites from the Norwegian military. The launch was delayed several times due to weather, but it finally lifted off in the evening of March 30th. It didn't get very far. The vehicle looked off from launch, fighting roll and pitch oscillations as soon as it left the pad until it finally succumbed 30 seconds into flight. The rocket reached a peak altitude of about 500 meters, engines wildly gimbaling to keep it flying true before flipping end over end and heading towards the ground. The first stage engine shut off either by computer command or fuel starvation, and the nearly fully fueled rocket fell back into the bay next to the launch pad and exploded. Luckily, it had pitched far enough downrange to not fall on the pad. No word about the local herring. Amazingly, ISAR Aerospace described this gymnastics-performing failure as a complete success. Commercial space is something different. This flight was the first orbital launch from Europe, and our team all agrees this is the prettiest launch site out there. On April 1, a day I would not want to fly to space, 4 space tourists launched from Kennedy Space Center on a Falcon 9 into polar orbit. This is the first time humans have orbited over the Earth's poles, and all of the flight's adventurers are interested in polar science. This is an ongoing mission, and we will be looking at it in more detail in our next episode once we know that everyone is home safe. We track launches with the help of RocketLaunch.live. So far this year, the United States has had 42 launches, China has had 19 launches, New Zealand has had 5 launches, Russia has had 3 launches, French Guiana, India, Japan, Kazakhstan, Norway have each had 1 launch. This makes the total number of launches so far this year 74. Finally, there are 10 toilets in space. Before we go, I would like to announce the possible death of supersymmetry. Since I was old enough to read about particle physics, I've been reading about how one possible set of solutions to explain why we have the particles we have in our universe would require the existence of a massive zoo of particles that bring the population of integer spin bosons and half integer spin fermions into symmetry. Quarks would be paired with squarks, neutrinos with sneurinos, gluons with gluinos, W bosons with winos, and B bosons with binos. It is all really a bit ridiculous. And for as long as I've been old enough to be reading about particle physics, folks have been predicting that the next update to this or that particle accelerator should allow the lightest mass supersymmetric particles to be discovered. With a decade of discoveries from the ATLAS and CMS detectors on the Large Hadron Collider behind us, researchers are starting to say that it may be time to admit supersymmetric particles, as they've been predicted, just aren't out there waiting to be discovered. May this theory of far too many particles rest in peace and torture students no more. Okay, now do string theory. Good night, everyone, and remember to go out and look up. Thank you so much to all our patrons who make this show and everything we do at CosmoQuest possible. We wouldn't be here without you. Links to our Patreon, Discord, and more can all be found in the show notes. Check it out, join the community. Oh, and click that like and subscribe if you want more science in your life.